I'm Professor Tridibesh from Netaji Subhash Engineering College, and I'm about to give a lecture on the dynamic characteristics of SCR. Now, in my first resource creation, I have dealt with the basics of SCR and the static VI characteristics, and here I will deal with the next part of the SCR characteristics, that is the dynamic characteristics of SCR. I've already told that there are two types of SCR characteristics: the static VI and the SCR dynamic characteristics. In dynamic characteristics, there are again two modes of operation. The first one is the turn on mode, and the second one is the turn off mode. Now first I will go into the switching characteristics during turn on mode, and for this I will take help of the block diagram which I have previously dealt with. Now you see a forward bias thyristor is, forward bias means what? The anode is positive and the cathode is negative. A forward bias thyristor is usually turned on by applying a positive gate voltage between the gate and the cathode. There is however a transition time from the forward off state to forward on state. This transition time is called the thyristor turn on time, and is defined as the time during which the thyristor changes from forward blocking state to forward conduction state. The turn on time is again divided into three parts. The first is the delay time or TD, the second is the rise time TR, and the third is the spread time denoted by TP. This three time intervals constitute the turn on time. Okay, now first I will deal with the delay time TD, this part. Now the delay time TD is measured from the instant at which the gate current, this gate current, reaches 0.9 G, that is 90% of Ig, to the instant at which the anode current reaches 0.1 Ia, 0.9 Ig, 0.1 Ia, where Ig and Ia are respectively the final values of the gate and the anode currents. The delay time may also be defined as the time during which the anode voltage, this anode voltage, falls from VA to 0.9 VA, that is 90% of VA, where VA is the initial value of the anode voltage. Now next is the rise time TR. This rise time is the time taken by the anode current to rise from 0.1 Ia to 0.9 Ia, that is 10% of Ia to 90% of Ia. The rise time is also defined as the time required for the forward blocking of state voltage to fall from 0.9 VA to 0.1 VA. And this part we can reduce this TR by applying a greater gate pulse. That is, the rise time is inversely proportional to the magnitude of the gate current and its build-up rate. As we increase the gate current, this phase gradually decreases. And the next part is the spread time or TP. The spread time is the time taken by the anode current to rise from 0.9 Ia to Ia, 90% of Ia to 100% of Ia. Or it can also be defined as the time interval during which the forward blocking voltage falls from 0.1 VA, that is 10% of VA, to the on-state voltage drop of SCR, which is around 1 to 2 volt depending on the rating of the SCR. Okay, so this, as now you see, we have already discussed that during turn on what happens, the current gradually increases, see, and the voltage across the SCR decreases. This is what is happening here. The current is increasing and the voltage is decreasing. Okay, now next we'll move another important thing here. We can see that the power loss basically occurs during the TR, that is the rise time, because here you are having some value of the Ia and again VA is also present, so this power loss Ia VA is maximum at this phase TR, so we need to reduce the TR. However, the main factor determining TR is the nature of the anode circuit. For example, for series RL circuit, the rate of rise of anode current is slow, therefore TR is more. For RC series circuit, di by dt is high, TR is therefore less. Okay, now next is the switching characteristics during turn off. This is the characteristics and this is the block diagram. Okay, now The thyristor turn off means that it has changed from on to off state and is capable of blocking the forward voltage. This dynamic process of the SCR from conduction state to forward blocking state is called the commutation process or the turn off process. Now once the thyristor is on, the gate loses control. We all know the latching current was there. So once it crosses the latching current, the gate is no more required. The SCR can be turned off by reducing the anode current below the holding current. Now if the forward voltage is applied to the SCR at the moment its anode current falls to zero, the device will not be able to block this forward voltage, as the carriers, that is the electrons and holes in the fold layers, these fold layers, the electrons and holes in the fold layers are still favorable for conduction. The device will therefore go into conduction immediately even though gate signal is not applied. Now in order to obviate such an occurrence, it is essential that the thyristor is reverse biased for a finite period after the anode current has reached zero. Now the turn off time, this is the turn off time denoted by TQ. The turn off time of the thyristor is defined as the time between the instant anode current becomes zero. So here the anode current has become zero, and the instant SCR regains forward blocking capability. During time TQ, all the excess carriers from the four layers of SCR must be removed. The excess carriers which are present here must be removed in order to make it completely turn off, that is to make it from turn on state or conduction state, forward conduction, to forward blocking state. Okay, the removal of the excess carrier consists of sweeping out of the holes from the outer p layer, this p layer, and sweeping out of the electrons from the outer n layer. The carriers around the junction J2, the carriers which are around the junction J2 can be removed only by recombination. The turn off time is divided into two intervals. One is the reverse recovery time, that is the TRR, this part, reverse recovery time, and the other is the gate recovery time, TGR. So your TQ is equal to TRR plus TGR. Now I have divided this TQ into a few instants denoted by T1, T2, T3, T4. Now at instant T1, anode current becomes zero. See, the anode current has become zero. After T1, the anode current builds up in the reverse direction with the same dIdt slope as before T1. The reason for the reversal of the anode current after T1 is due to the presence of carriers stored in the fold layers. The reverse recovery current removes excess carriers from the end junction J1 and J3 in between the instant T1 to T3. In other words, reverse recovery current flows due to the sweeping out of the holes from top p layer and electrons from the bottom n layer. At this instant T2, when about 60% of the stored charges are removed from the outer two layers, carrier density across J1 and J3 begins to decrease, and with this reverse recovery current also starts decaying. You see, this reverse recovery current which was increasing in this direction after T2 has started decreasing. The reverse current decay is fast in the beginning but gradual thereafter. Initially it was fast, but it is becoming gradual after this period. The first decay of the reverse recovery causes a reverse voltage across the device due to the circuit inductance. There is a reverse voltage due to the circuit inductance. This reverse voltage surge appears across the thyristor terminal and may therefore damage it. In practice, this is avoided by using protective RC element across SCR. At instant T3, at this instant T3, when reverse recovery current has fallen to nearly zero and N junction J1 and J3 recover, the SCR is able to block the reverse voltage. For a thyristor, reverse recovery phenomena between T1 and T3 is similar to that of rectifier diode. At the end of the reverse recovery period, that is from T1 to T3, the middle junction J2 still has trap charges. Therefore, the thyristor is not able to block the voltage after at T3. It cannot block the voltage at T3. The trap charges around J2, this trap charges around J2, that is the inner two layers, cannot flow to the external circuit. Therefore, these trap charges must decay by recombination. This recombination is possible if reverse voltage is maintained across the SCR through the magnitude of this voltage is not important. The rate of recombination of charges is independent of the external circuit parameter. The time for the recombination of charges between T3 and T4 is called the gate recovery. This time is called the gate recovery, and is denoted by TGR. That is, the gate recovery time is denoted by TGR, and it is the phase between T3 and T4. At the instant T4, junction J2 recovers and the forward voltage can be reapplied between the anode and cathode. The thyristor turn-off time TQ is in the range of 3 to 100 microsecond. The turn-off time is influenced by the magnitude of the forward current, dIdt at the instant of commutation, and the junction temperature. Now, an increase in the magnitude of these factors increases the thyristor turn-off time. If the value of the forward current before the commutation is high, trap charges around junction J2 are more. So, the thyristor turn-off time TQ is applicable to an individual SCR. In actual practice, the thyristor form a part of power circuit. The turn-off time provided to the thyristor by the practical circuit is called circuit turn-off time and is denoted by TC. Circuit turn-off time is denoted by TC. It is defined as the time between the instant anode current becomes zero and the instant reverse voltage due to practical circuit reaches zero. Time Tc must be greater than Tq for reliable turn off, otherwise the device may turn on at any undesired instant, a process which is called commutation failure. So this was the turn off part, and this is the whole characteristics which includes both the turn on and the turn off characteristics. That is called the dynamic characteristics of SCR. Thank you.